Welcome back, 143ers. This lesson here is on chapter 23 on spherical mirrors and trying to deal with them mathematically. And so we'll try to develop some sort of equations that will help us give us some precision here. So I'll call this the spherical mirror equation. And so it's important to go through, the first part on ray diagrams, because for the most part, that's what we're going to start here with. And that's going to allow us then to really kind of come up with the mathematics that we might need here to be able to do this in a different fashion. So maybe not better, but at least differently with more precision here. Okay, so I just have a spherical mirror here with some objects out in front, and I'm just going to say that, maybe just to make life easy, let's have this be right here, be the focal point here. Okay, and so if I get that distance and I double it right about here someplace is the center of the circle or something like that. And I'm just going to draw some ray diagrams here. And well, let me kind of draw a ray. I think we called this ray number 2 in the previous lesson. Some information comes from the top of the object and goes to the focal point, hits the mirror, and will come off, in some sort of parallel fashion. And so, that ray is going to look something like this. It's going to hit this mirror, and then it's going to come off here parallel, something like that. And so that was ray number 2 that we drew before. And I kind of like that ray because I really kind of have an idea in the back of my head what I want here. And what I really want is exactly what we had in the thin lens situation, that if I put an object someplace away from a lens, I know that object distance, I want this equation to predict where the image is going to be. And I want it to tell me whether it's real or whether it's virtual. And but I do need to give information on, in that case, the lens. And that information was the focal distance. And so here I want the same thing, that if I tell you the focal distance of the mirror and where the object is, can you supply me information about where the image is going to be formed? And by drawing this right here, I'm kind of in the back of my head seeing that maybe I'm getting focal points to be, kind of part of the situation here. And that's kind of really what I want. And so I'm going to draw a ray right now that is not one of the principal rays that we drew last time. But once again, I kind of have an idea of what I kind of want to see come out of this equation. So I'm trying to get those different parameters involved here. And but the 3 principal rays are all essentially just the law of reflection. So it prevents us from having to draw on a normal line, measure the incident angle, and then copy that on the other side of the normal line and call that the reflected angle. So these are just quick little rules of thumb. And so I'm going to have a light ray hit right here because really all distances are measured from that spot from the mirror, right? So where the object is to that little blue dot that I just put, that's really DO. That's the distance that the object is right from that spot, and that's right, on the shiny side of the mirror. So I want that to be involved here too. So I have a light ray that comes in here from the top of the object and hits that spot, then what I'm going to do is have to measure that angle right there and then copy that angle down here for the reflected ray. And so this is going to be theta as well right there. And what I've got then is an image that is being formed right here. Okay, so I have a real image here. And I think just to make life a little bit easier to kind of see what's going on here, I'm going to start looking at some different triangles here. So I'm going to call that point A. I'm going to call that point B. And I think I'm going to call this right here point D. So C is already kind of used up for the center of the sphere that has been used to cut this arc that we're making the spherical, or this sector of the spherical mirror here out of. And I think I'll keep calling this, I'll keep calling that point F here. And so I'm going to call this point right here A prime. I'll call that spot right there B prime. Because you can see that they kind of correspond to A and B. That is A to B. This right here is really the height of the object. And this right here is really the height of the image. And so I'm going to call that, point A prime and B prime. And maybe I'll call this spot down here. Let me see, we got F, so I'll have to call that point G, I guess, something like that. Okay. And so let us start by looking at, look at this triangle right here. So I'm going to put some little yellow lines in here. This is going to get kind of cluttered looking here in a little bit, but those two triangles right there, they're not the same triangle. They're not congruent, but they are similar. And I know they're similar because they both have right angles in them, and they share this angle right here that I'll call maybe alpha. So they have all three angles the same in them. And then, if I kind of look this side right here that I'm kind of scratching out of black, that looks like the same size as what's here. So that might be, HI sitting over there. But, those two triangles are similar. And so I've got some proportions I can write down. But it looks like, one triangle sitting like this. And that's got A, B, and I'm looking at my diagram, D. And from A to D, this is really the distance that the object is. Here's the height of the object. And then the other triangle that is similar to that, let me see. No, I'm looking at this other triangle. So let's back that up. Yeah, I'll eventually get to that one here too. Let me redraw that here. What I've got is this triangle right here. That's got point A, B, and it comes down here to point F. Okay. And so this is the height of the object. And this distance right here would be the distance that the object is minus the focal length, right? So the full distance to the mirror is DO. Then I subtract the focal length, and it leaves me just this little piece right there. Okay, so I've got that triangle, and then the other triangle I'm looking at has point D. I'm going to turn it right side up to point G, and then it goes out to point F. And it's got this right angle right here. And so this is the height of the image in that triangle, and it's got the focal distance in it. Okay, so I've got those two triangles that are similar to each other. So I should be able to say something like this piece, HO, is to that piece, HI, as this piece, DO minus F, is to F. And so I think that's exactly what I'm going to say. So I'm going to look at those two and say something like HO all over HI equals DO minus F all over F. And at that point, I've got now an equation And it's got some really good information in it, but it doesn't have what I want. It doesn't have the image distance in it yet. So, so we still need to get that. But it does have where the object is, and it has the information on the mirror, that is how much curvature it has, which is the focal distance. And I could turn that into a radius just by multiplying by 2 very quickly if I'd like to. And so I think what we need is a little bit more information here, but this is pretty good, what we've got. And so now I'm going to come back up to this diagram, and I'm going to look at this triangle right here, because I still need where the image is being formed, and the image is being formed here. So I'm going to look at maybe that triangle, and yeah, I kind of like that one. And which other one do I need here? I think I want this one right here. I think I want that one right there. So those two are similar to each other because they both have right angles in them. So let me kind of, draw these out again a little bit here. And so we've got point A, we've got point B, and then we kind of come down here. We have a right angle, and we have this angle theta in it. And this is the distance that the object happens to be. And here's the height of the object. And then the other triangle, and this is point D right there. The other triangle is point A prime to point B prime. And so if I were to get it oriented the same way, right at A prime is the right angle. And then it's got this angle, the same angle theta, because it has to be the same angle from the law of reflection. This is the height of the image, and this is the distance that the image is being formed from point D to A prime. So it looks like I've got 2 primes there for some reason. And so they're not the same triangle, they're different sizes, but the angles are the same. So that just means one triangle is a kind of a blow up of the other triangle here. And so once again, it looks like I could say something like this piece is to that piece, HO is to HI, as this piece is to that piece. And so what I should be able to do now is get really some kind of working equation by combining these. So I have HO equals HI equals a bunch of garbage in the first set of triangles. Then I've got HO over HI equals some garbage in the other one too. And so I think then I should be able to use, what your math teachers would call the transitive property. Well, if A equals B and B equals C, then A equals C. And so there's our equation. It has exactly what we want. We put the object distance in. We have some information about what kind of mirror it is. That is its focal distance. And the image then is sitting right there in front of us. And so this doesn't look great to me, but it's not bad, right? It is workable. I think what I'm going to do, I'm going to divide everything by, looks like DO is what I really want to do here. And so I really have here, DO all over F, and I'm going to divide that by DO. And here I really have 1, right? I really have F all over F. I'm going to divide that by DO, and then I'm going to divide, this one by DO as well. And so those will cancel, and it leaves me this right here, 1 over F, and this right here is 1 over DI, and then I get this right here, F over F cancels out, so I have 1 over DO, and I bring it to the other side of the equal sign, and I got that right there. And you should really right now at this point be gasping for air and be saying, oh my God, That is just unbelievably remarkable. What the heck is going on here? Because this equation is coming to us from the law of reflection, but we've seen this equation before. And this is called the spherical mirror equation. And it looks precisely like the thin lens equation. One time in the lens case, this equation came out by using Snell's law, essentially. And now what I've got in this yellow box is coming to us from really the law of reflection, not the law of refraction. And yet we get exactly the same equation. And it really is just a coincidence. There's really nothing, excuse me, deep underlying physics here or anything, exit that should give you any sort of existential crisis or anything like that here at all. So there's really nothing here that's too dramatically important. It's just very, very coincidental that the two equations come out to be exactly the same, even though they are based on completely different physics. One's based on light going through a transparent material, and here this is light bouncing off of some sort of silvered material, some sort of reflective material, and yet the equations come out to be exactly the same. Now, in both cases, both equations are approximations, and if you were really paying attention in this derivation, you might see exactly where the approximation is. If you didn't see it, it doesn't really matter. This is good enough for people making telescopes. This will be good enough for us. So this will work out very, very nicely here. Okay, so now DO, that's the distance that the object is from the mirror. That kind of makes sense. DI is the image distance, and then F is the focal distance. But we have two types of mirrors here, right? We could have a mirror that is like that, where the object's over here, or we could have a mirror like this, where the object's over here, right? In the first case, it's concave. In the second case, it's convex. And, I derived this equation for a concave mirror. Does it make a difference? And it really doesn't. And so when you start working with this equation, what I would do, and I'm looking in your textbook, if you have the latest edition, on page 655, he has a sign convention, and that sign convention will tell you exactly what you need to be doing here, because a plus or minus sign here incorrectly done is kaput for everything. The whole thing will just blow up on you. And so he says right here, when the object, the image, or the focal point is on the reflecting side of the mirror, the corresponding distance is positive. Okay. And so I think what he just said is that this is a positive focal length of mirror. The focal point is on the reflecting side of the mirror. Yeah, the focal point here is on the reflecting side of the mirror. On the convex mirror, the focal point is on this side, but this is the reflecting side here. And so this is going to be a negative focal length. So I can tell the equation what kind of mirror I got by either putting in a positive focal length or a negative focal length. But it looks like concave mirrors, if they're concave, they are a positive focal length, and if they are convex, they will have the minus sign. And that's how we're going to tell the equation the difference between one and the other. So he says, when the object, image, or focal point is on the reflecting side of the mirror, like it is with the concave mirror, the corresponding distance is positive. If any of these points is behind the mirror, the corresponding distance is negative. The image height is positive, the image is upright, and it is negative if it's inverted relative to the object. Okay, That kind of makes sense here. And so we're forgetting a couple things here, or just we haven't quite got to them yet. But this is kind of good to kind of keep in mind, right? So anytime I'm using this equation, I think I'm going to have page 655 kind of open right in front of me here. And I'm going to take a look at, this derivation up here. And this right here, right, should be signaling something to you. How big the object is in relation to the image, that's really what we call magnification, right? But magnification is not H over HI, it's really how big is the image in relative proportions to the object. We can use that here, just like we did before, and say that our magnification is HI all over HO. That's what we want to define as magnification. How big is the image compared to the actual object? So if the image is 2 times bigger than the object, we're going to get a number here of 2. Right? But notice H over HI equals D over DI. So I'm just looking at this right here. So if I take the reciprocal of that, then this is going to be equal to di all over do, and we have to put in this minus sign just like with lenses because things can get turned upside down. So that minus sign comes from his sign convention. So with that minus sign there, if we follow the sign conventions, then objects that are actually upright and creating an upright image will give us then a positive number here because those will be virtual images. The real images will give us the inversion then. And so that minus sign is to match up with his sign conventions. So we had to have that in there. Okay, but so this is magnification. And then for spherical mirrors, remember that right there, if I multiply the focal distance by 2, it always tells me the radius of the circle. And so that's true just for spherical mirrors, but that's the only type of mirror that we really deal with here. Okay, and so there's really not a lot of moving parts here, right? The equation, the spherical mirror equation, is identical to the thin lens equation, and it works exactly the same. He's got a sign convention that's very convenient. So if you learn that for the lenses, it works pretty much the same way here too. That's kind of good news. And I think about the only thing you have to really pay attention to is just kind of getting used to that sign convention and seeing exactly what the signs tell us and things like that. So you do have to be careful here because a wrong sign here will just completely destroy any sort of numerical solution that you're really trying to do here. Okay, we also have this idea of magnification. How big is the image compared to the object? And so we have the magnification there, and the mirrors, we can see from the ray diagrams can make something bigger or smaller and things like that. So that will always be part of the description for the image as well. So I think probably in your package of stuff, you might have something that looks like this, and so it's probably time for us to get something like a calculator, and then start looking at some of these word problems here. And I'm going to be armed with page 655, the sign conventions right in front of me. And, I've got these here I can refer to if I need to. But for the most part, they look just like they were for lenses. So, maybe I don't really need to look at those too much at all here. But let's start taking a look at some of these word problems here and see if we can't, put this stuff to good use here and have some precision now in our solutions. So I'm just going to start here with number 1. And it says a concave mirror. Okay, so that's important because now I already know that the focal length is positive, right? So I already kind of know for a concave mirror, the focal length is positive. And the focal length is 10 centimeters, right? So it's going to be plus 10 centimeters. Locate and fully describe the image of an object that is placed 25 centimeters from the mirror. Okay, so I've got something like this. that I'm going to be working with. And that focal distance here is a positive 10 centimeters. I'm just going to use those units. And in this case, the object happens to be 25 centimeters from the mirror. Okay. And so the object distance is going to be probably a positive almost all the time, unless I've got a combination of lenses and mirrors or something like that. That might not be the case, but it needs to be on the shiny reflective side here. So that's going to be a positive distance in this case. And so that's what I've got to solve for DI. So now it's time to go to the calculator. 10 minus 25 equals. And I think I'm getting this. I think I'm getting DI here equals, and I'm getting positive about 16.7 centimeters. Okay, now let me see if this makes sense. I got a focal distance of 10 centimeters, and the object is 25. So the object is far from the mirror in terms of the focal distance. And I get an image distance, and it's positive. So now I'm looking at the sign conventions. It says the image distance is positive if the image is on the reflecting side of the mirror. So the image is on the reflecting side of the mirror. And so I'm going to go backwards in time here. So who says time travel is not possible? And I'm going to go back to a concave mirror. And that looks like the first diagram that we have here. I have an object in that first diagram that is well outside of the focal distance. And what I created was an image that was on the reflecting side of the mirror, right? So I see the reflecting side of the mirror, and the image is real. And in this case, he calls that a positive distance. So I see the ray diagram right there. So I should get here something that's going to be small. It should be inverted, and it's real. And that's exactly what we've got here with the mathematics. And so when we work this out, so this is real. This is a real image because of that positive sign. Now, we want a full description. So, I'm going to keep kind of going a little bit further with the mathematics here and say that magnification is minus DI all over DO. And there's this built-in minus sign, and DI I just found as positive 16.7 centimeters. And in this case, DO was positive 25 centimeters. Okay, so those will cancel out. So I'm going to get 16.7 divided by 25, and I get about 0.67. And there is a built-in minus sign here. And so there's this minus sign coming from here. And this tells me that it is inverted. And because the ratio is less than 1, it is minified. And so now I have my full description really with the precision that I want. I know precisely where the image is being located, which means that's exactly where I put a piece of paper, and then I'd be able to look at the piece of paper and I'd be able to see the actual object being reflected from the mirror, and I'd have something that looks pretty clear to my eye, and I'd be able to see that here. It's going to be upside down, and it's going to be smaller than the object happens to be. And as I kind of zip backwards in time again here, and I look at that first ray diagram, that's exactly what we see here. A real image that gets turned upside down. The image is upside down or inverted from the actual object, and it's smaller and it's real. And so that first ray diagram is really coming to life here with the mathematics exactly in this example. So, and so this is, this looks pretty good to me here. So the math matches up with the ray diagrams. And it looks like maybe I didn't really read the problem enough here. There's a part B and there's a part C here. Okay, so part A, the concave mirror has a focal length of 10 centimeters. Locate and fully describe the image if it's 25 centimeters from the mirror, and that's what we just did. There's a part B. Describe the image if it's placed 10 centimeters from the mirror and if it's 5 centimeters from the mirror. So that's pretty close to what we did in those first 3 ray diagrams. So I have, you know, the first option where the object is outside of the focal point. Part B, it looks like it's right on the focal point, and then part C looks like it's actually on the inside of the focal distance. And so, you know, looks like they want us to, you know, solve those. And so, okay, let's go ahead and do that here. So on 1, part B, we have this to solve, and our focal distance here is positive 10. Okay. And the object now is positive 10 centimeters away. And we are trying to predict exactly where that image is going to be located. And now, you know, when I take this math up here and I have really 1/10 minus 1/10 equals 1 over di, right, this is a 0. And so, you know, the image distance needs to really be at an infinite distance away here. And so there is no image being formed. There's really no mathematics that gives us any sort of precision here. And so here, just like in the ray diagram that we did in the previous lesson, there is no image formed. Okay, and so, you know, I suspected that was going to happen because I just refreshed my mind with what took place with the ray diagrams up above. Now in part C, we have exactly the same mirror, but now the object is 5 centimeters, right? 5 centimeters from the mirror. So let's see what happens here. Okay, so in 1, part C, here is my spherical mirror equation. I've got exactly the same mirror, so it still has a positive focal length of 10 centimeters. And now the object is 5 centimeters away, and I want to see where that image is going to be formed. And so I'm just going to kind of do this on my calculator. And I think I get minus 10 centimeters here. So let me try that again. It's always worthwhile to check these. Yeah, I think I get the same thing twice. So either I'm doing the same dumb thing twice, or this looks good. Okay, so so there is my image distance. Okay, and if I want to fully describe the image here, then I'm going to do a magnification. Magnification is minus di all over do. So there's a built-in minus sign, and di is minus 10 centimeters. And do was positive 5 centimeters. So centimeters cancel. These two minus signs will cancel. And now it looks like I get positive 2. Okay. And so what I have is an upright image. This ratio is bigger than 1, so it got bigger. So it's magnified. And this minus sign up here tells me that it's virtual. And so I'm looking at the sign convention, and that's exactly what you know, the plus and minus signs here really mean. So if I get an object inside of the focal distance, it looks like it should be upright, magnified, and my mind will be perceiving this thing as being behind the mirror, just like sort of in the morning, you know, when you sort of look at yourself in a flat mirror. And I think that's this last diagram here that we did for a concave mirror. In the last lesson, the object is right there, and it's closer than the focal distance, so it's inside the focal distance, we get something that's virtual, it's upright, and it's magnified, and the mathematics tells us exactly the same thing, but now we've actually got numbers to go with that. Okay, so when I kind of come down here and take a look, see here, this all looks like really pretty good to me. You know, all three cases matched up with the ray diagrams very nicely. That's why it's so important to follow the sign conventions so that we get exactly the same descriptions here. Okay, so if you've got some practice, you know, using the thin lens equation, this isn't really too much difference, and so that really kind of makes it nice here. Okay, so let's take a look and see if this gets any worse for us here at all. Number 2, it says a car's rear view mirror forms an image of a truck located 10 meters from the mirror. Okay, so that's my object distance. The focal length of the mirror is 0.60 meters. Fully describe the image of the truck. Okay, so the truck is located 10 meters from the mirror, and this rear view mirror is forming an image of it. So I've got 10 meters, and I got a focal length of 0.6. Okay, so let me get some space down here to write on, and I think I'll just go right here. Okay, now a rear view mirror. Now you just have to think this through, and so just you know, don't just blindly start putting stuff into equations and so forth. The rear view mirror must be a convex mirror because that was the only mirror that never turned something upside down, right? There's no way that an engineer is going to put something in your car that's going to turn things upside down. So this must be convex. And your textbook says this has a negative focal length. So I'm going to go to the mirror equation. I'm trying to find this image. And so I'm going to tell this equation that my focal distance was, I believe, 60 centimeters or 0.6 meters, but I've got to put the minus sign in, and so yeah, 60. And I probably lost that, so okay. 0.60, and the object is 10 meters from the mirror. And this is what you want to solve for DI. So convex mirror, I've got to tell the equation that it's got a minus sign here. So go to your calculator. And I think I'm getting this. This looks kind of suspicious to me, but I'm going to try this again here. A minus sign and 0.57 meters. So my first best guess is that 0.6 minus 10. Well, I'm getting the same thing here. Okay, so I think that looks probably okay then. So I'm getting about 0.57 meters is my image distance. And so let's take a look at what's going on with magnification here in a moment. Now the image distance is negative. So when I'm looking in the textbook, when the object, image, or focal point is on the reflecting side of the mirror, the corresponding distance is positive. This is not positive, this is negative. And so it's behind the mirror. So this is then behind the mirror. That means it's virtual. It's a virtual image. And so I'm going to go to magnification is minus DI all over DO. We have a built-in minus sign. And DI in this case is 0.57 meters with a minus sign. And DO is positive 10 meters. Okay. And so this minus sign and that minus sign are going to undo each other, but 0.57, oh, divided by 10, yeah, I have to do that on the calculator. That's 0.057, and it's positive. Okay, so it's upright and really highly minified. Okay, so objects in the mirror are closer than they appear because this mirror, because of its shape, makes things smaller, and your brain thinks things that are small are far away, and it's not upside down, so it's upright. And so I think if we go and check with our ray diagrams, any picture with the convex mirror gave us a virtual image, and it was always upright and it was always small. And so the mathematics does exactly the same thing. And so, that's good. As long as I didn't make any mistakes on the calculator, I think this is the way this is going to really kind of work out here. And that leaves us, maybe one last one that you had in your package of stuff. An object of height 2 centimeters is placed 30 centimeters from a convex spherical mirror of focal length 10 centimeters. Okay. An object of height 2 is placed 30 centimeters and the focal length is 10. Okay. So it's placed 30 and the focal length is 10. And the object had a certain height in this case. So let me kind of go back and grab that height. It was, the object has a height of 2 centimeters and it's a convex mirror. Okay. So the height of the object is 2 centimeters. And it says it's convex, right? So it's a convex mirror. So because I see that word convex, I'm going to have to tell the equation I need a minus sign in front of that focal distance here. And so that's the information that we have. An object that's 2 centimeters high, so it's getting close to about 1 inch high, so it's something not very big, is 30 centimeters away from a convex mirror. So if this is the object, is my finger, the mirror is shaped like this, right? So it's the outside of the spoon, right? If you get something like a spoon, it's the outside of it, it's not the inside of it. That would be concave, and so this is convex here. Okay. And what we want to do is find where the image is going to be formed. Okay, so that's just going to come right from our spherical mirror equation. And I'm going to put in a minus sign here. For my focal distance, I'm looking for DI, and DO is plus 30 centimeters. So it looks like we're going out to like 3 sig figs or something like that. So, okay, so 10, the minus sign, minus 30 equals. And I think I'm getting here that DI in this case is minus 7.50 centimeters. Okay, and so it's virtual. And with a convex mirror, that is just always the case. There's no other way that this could really kind of come out. And my magnification is minus DI all over DO. It has a built-in minus sign, and DI is minus 7.0 centimeters. And in this case, DO was plus 30 centimeters. So the centimeters will cancel. And leaves me with the magnification with those two minus signs canceling out. It has positive. So 7.5 divided by 30, that's just 1/4. Okay, so it's upright. That's a plus sign. And this is less than 1, and so it's minified. Okay, so there I think we have it. So we know where the image is coming from, or our brain is interpreting that the light rays are coming from some place like 7.5 centimeters behind the lens. And they're not really coming from there, right? They're not, excuse me, the lens, the mirror. It can't be coming from behind the mirror, but our brain is telling us that. So this is where the light rays appear to be coming from, and they're coming from something that is upright and smaller. And I don't think there's really anything else that we had to do on this one, so I'll come back to that here in a moment. Is the image upright or inverted? Yeah, find the height. Oh, find the height of the image. Okay, so let's do that, height of the image. Okay, and so there still looks like maybe a little piece here still to do here, but everything here is so far pretty good. And I'm going to recall that magnification is minus di all over do, or hi over ho. And my magnification here is a number that I know, and that's plus 0.25. And the object, its size was something that we were told. We were told that the object was 2 centimeters big, right? So I'm going to put in 2 centimeters here. And notice that when I get 2 centimeters and I multiply it by a 1/4, it's just going to tell me how big the image is. So we know it's minified, right? So, so this is how big this image is going to be. So 1/4 of 2 is how much? Like 0.5 or something like that, right? So this is going to be positive 0.50 centimeters is the height of the image. So, which is 1/4 the size of 2 centimeters. So 0.5 plus 0.5 plus 0.5 plus 0.5 gives me 2. So 1/4 of that is going to be this number here. And so, yeah, I've got something that is smaller. It's been cut down to, 25% of the size that it was before, but it's still upright. And so this gives us the full description here. So once we've kind of tackled lenses, this doesn't seem too bad here, because really most of the physics and the processes here are running much in the same way. And so all we really did was trace the straight lines that are created by light reflecting off of the surface, and it created some triangles, which then allowed us to come up with this thin lens, the spherical mirror equation. And so that allows us to do all of these predictions of exactly what the light rays will be doing. Then we get descriptions here of exactly what those images happen to be. So, yeah, hopefully this is making sense, and this helps you through, that last part of chapter 23 dealing with spherical mirrors. And so from this point, we'll start looking at different properties of light. And so this is called geometric optics, mirrors and lenses. And now we're going to start looking at some different aspects in chapter 24, and that'll be called physical optics. So that will be based on the physical properties of waves, without really instrumentation here. Right here, we've got a shiny material shaped like a spoon or something like that, a spherical mirror, or we have a lens which is made of some sort of transparent material like glass or plastic or something. And so now we're just going to look at the physical properties of light in terms of interference and diffraction and dispersion and those types of things. So some very nice physics showing up in chapter 24. And once we've got a couple of those ideas kind of under our belt, then we'll take a look at some optical instruments, like probably the human eye. We'll look at maybe simple telescopes, which shows up in chapter 25. So that's what we're heading for probably the rest of the month of March, and then we'll be starting some topics in modern physics, and seeing exactly what's going on with physics today, and so forth. So hopefully this helps you out. Don't forget, have those sign conventions in front of you when you're trying to solve these problems. That's always a great help here. And I will see you soon. So give this a shot, get these going. And I think probably most of the mirror stuff should go pretty quickly for you. And I do recall you have an example, uh, probably in the lens section of this chapter, where you had a lens and a mirror being used in combination. And so you might want to, see if you can't work that out and see what you get. I haven't worked it out yet, but I think I know the process. And so light's going to go through that lens, form an image. That image will be the object for the mirror. And so, now I can probably just go from there. So give that a shot and see what you get. And we can kind of check your answers in something like discussion time or something like that. Okay. So hopefully this helps, and I'll see you soon.